Hi, and sorry for breaking the audiovisual stuff, but hopefully this works. Yeah, so I'm Reese, and I'll be presenting our work, MC Mutants, which is about evaluating and improving testing for memory consistency specifications. And this is joint work between UC Santa Cruz and Google. So let's start with some highlights. So in this paper, we developed a way to evaluate the effectiveness of memory consistency specification, or MCS testing, as well as develop new testing techniques. And we hope that this work brings some more rigor to the field of memory consistency specification testing. We evaluated our methodology on 4 GPUs in WebGPU, which is a new GPU browser for the framework, or new framework for GPUs in the browser. And our impact, we discovered 2 new bugs. One in a message passing idiom on AMD GPUs, which led to a compiler fix by AMD and a change to the WebGPU specification, as well as a coherence issue on Intel GPUs on MacBooks, which has been reported to Apple. Finally, we integrated comprehensive MCS tests into the official WebGPU conformance test suite, which must be run by many major browsers as part of their WebGPU development efforts. So what is a memory consistency specification? It defines the allowed behaviors of a shared memory parallel program, and most modern processors implement relaxed MCSs, which allow weak behaviors, or behaviors that you cannot describe using sequential consistency. An MCS is implemented by a parallel programming framework, which may consist of a language, compiler, and architecture runtime. MCSs are also defined formally, axiomatically, using events and relations between those events. And these formal MCSs can be used to synthesize MCS tests, which in turn you can use to test parallel programming framework implementations. Now, these tests are inherently non-deterministic due to their parallelism, so they have a large state space of test outcomes. And the inner blue circle there represents maybe the state of the art of MCS testing, where you're exploring some of the state space of test outcomes, you're finding some bugs, but you might be missing other bugs. So the question is, how do we get from this upper set of circles where we're exploring a limited state space of test outcomes to the lower set of circles where we are exploring a larger state space and finding more bugs, as well as providing more confidence in our implementations. So our methodology is to use mutation testing. So normally in mutation testing, you have some code and you have tests that check the code, and then you mutate the code in some way to introduce a bug and check whether or not your test actually finds that bug. We do something similar, but in a way applied to the tests themselves to evaluate the effectiveness of our testing strategies. So starting from conformance tests, which look for bugs, disallowed behaviors by the MCS, we mutate those tests to create mutants based on the formal definitions of memory consistency specifications. And there's 2 important things here. One is that in these mutants, they're looking for allowed but weak behaviors in the MCS. So these are behaviors that should be observable, but in many cases with state-of-the-art strategies, they're not observable. Also, because we're using these formal MCSs and we're defining the mutants as related to the conformance tests, the buggy behaviors in the conformance tests are very similar to the weak behavior in the associated mutant. Now, we get to this stage and we realize we're not observing all these weak behaviors that we should be able to see. So this allows us to come up with new novel testing techniques such as parallel testing, which allow us to explore a greater state space of test outcomes, see more weak behaviors. The final step then is to translate those mutants back into the associated conformance tests, which allow us to find new bugs and provide more confidence in the MCS implementations. So this is a pretty high-level overview of what we did. So I'm now going to go into some details around what this actually looks like in practice. But in order to do that, we first need some background on what an MCS actually looks like. So this is an example of a message passing litmus test. You have on one thread a store to a data variable and then a flag variable. And on another thread, you have a load of the flag and a load of the data. And these release acquire fences in between each of those instructions disallow this behavior, where R0 equals 1 and R1 equals 0. Now, this can be represented as a candidate execution. Here, there's events, which are the writes, and relations between those events, and the reads. And all of these relations have names. So program order, or PO, relates events on the same thread. So you can see here that A, B, and C are program order related, as well as D, E, and F. There's also communication events, like reads from and from reads. So reads from relates, you can see it here that C and D are reads from related because D reads the value that C wrote. Similarly, A and F are from reads related because F does not read the value that A wrote, so we can infer that F must occur before A. There's also a synchronizes with relation. So a synchronizes with relation specifically relates a release write with an acquire read. Here, because there's a release fence in B before the write in C, C is promoted to a release write, and because D is a read before an acquire fence, it is promoted to an acquire read. Therefore, you get this synchronizes with relation between C and D. Altogether, you can use these relations to create a relation called happens before, which intuitively describes the order in which events should appear to happen, and is formally defined as the transitive closure of the union of program order and synchronizes with. A read must return the most recent write as determined by happens before. So if you look at this execution, because there's this chain of happens before relations between A and F, but F does not read the value that A wrote, we know that this execution is disallowed by the MCS. So what do? We take these disallowed executions, where here I've just changed data and flag into X and Y, and we mutate them by disrupting one of the relations. So in this mutation, we're disrupting the synchronizes with relation by simply removing one or both of the fences on either of the threads. You can see that there's no longer a synchronizes with relation between C and D, which correspondingly means there's no longer a happens before relation between C and D. Now, on this execution on the right, the behavior where F reads 0 is allowed. It's a weak behavior in the MCS. So this is how we transform disallowed buggy behaviors in conformance tests into weak but allowed behaviors in our associated mutants. We don't just do this for one test, we do it for a bunch of tests, and in the paper we describe a variety of different templates. So here you can see that A is an abstract memory event, F is an abstract memory event, and the relation between A and F is an abstract communication relation. When you actually concretize this template into the message passing example, you translate A into a write, F into a read, and therefore the communication relation becomes from reads. Also, C and D must be a write or an RMW or a read RMW respectively in order to get that corresponding synchronizes with and happens before relation on the right there. In the paper, we describe 3 of these types of mutator functions, which leads us to generate 20 conformance tests and 32 associated mutants. Now, once we created these mutants, we realized that we're not seeing as many of these weak behaviors as we should be able to see. And this is because previous testing strategies use a single instance paradigm where you have one thread that runs the stores of the test and one thread that runs the lows of the test. So based on this insight, we generate a parallel testing strategy which greatly increases our ability to see weak behaviors. And in this strategy, every thread runs stores and loads for both half of the litmus test, and they're paired up in a way so that every litmus test is complete. And we get a lot greater throughput, we get a lot greater stress on the memory system, we can see a lot more weak behaviors. In the paper, we go over more how we do this while avoiding control flow and having a low instruction overhead so that it actually scales well to parallel hardware. So we evaluate our work on 4 GPUs, and in one from NVIDIA, AMT, Intel, and Apple, and we calculate a bunch of different metrics. So one is mutation scores, which is the percentage of mutants where weak behaviors are observed. Another is a correlation analysis, which correlates buggy behaviors in conformance tests to the weak behaviors in the associated mutants. We also calculate mutant death rates, which is the rate at which weak behaviors are observed in the mutants. And we come up with a MCS test confidence score, which is a statistical score measuring the trade-off between time and reproducibility when you're actually testing, and this has implications on how you integrate these tests into a conformance test suite. I won't have time to go over all of these right now, but I'm going to briefly go over mutation scores and correlation analysis. So this graph shows the mutation scores finding weak behaviors in mutants using different strategies. So single instance test environment or site baseline is basically a very naive strategy where you run one instance of the test with no added stress on your memory system. And you can see the mutation score is pretty low, 6%, which means you don't see very many weak behaviors. Site, single instance test environments, this is basically previous state-of-the-art strategies, achieves a mutation score of 46%. So okay, but we could do better. So parallel test environments, or PTE baseline, is just our parallel test environments without any previous state-of-the-art added stress, and it achieves a mutation score of 73%, while when you combine previous state-of-the-art strategies with our parallel test environments, we can achieve a mutation score of 84% across the 4 devices we test. We also want to show that these bugs and weak behaviors are actually related. So we perform a correlation analysis in the paper where we relate the rate at which weak behaviors occur in mutants to the rate at which buggy behaviors occur in conformance tests. We do this for the 2 bugs we found in our study, the one on Intel and AMD devices. we also reproduce a bug from a previous study which was found in NVIDIA devices, and we calculate the correlation scores. The Pearson correlation coefficients, which are shown on the right here, they're all pretty high, above 0.8, so we can reasonably conclude that there's a strong association between finding weak behaviors in mutants and buggy behaviors in conformance tests. And that's how we kind of get from this mutants back to the conformance tests in our original diagram there. So overall, today I introduced MC Mutants, which is a way to evaluate the effectiveness and increase the rigor of MCS testing. We basically applied mutation testing to formal memory consistency specifications. We designed a parallel testing strategy for devices like GPUs, and we found multiple bugs and contributed our tests to the Web GPU Conformance Test Suite. I also want to briefly mention we've developed a pretty cool tool called GPU Harbor, which you can actually use to explore your GPU's weak memory behaviors from the browser. So you go to this website, you can play around with all the types of tests, different types of weak memory tests, and see how they